Welcome to the new lecture on transistor hybrid models and multistage amplifiers. Today we will see multistage amplifiers. In the next lecture, we will analyze multistage amplifiers using hybrid models. So first thing is, what is a multistage amplifier? Okay. As you can see in the circuit that here there is a diagram which shows there is a first stage of amplifier which is connected to the second stage of amplifier, and likewise there are n amplifier stages are connected in series sequentially. So actually when we need this, say in case the voltage gain or the power gain from an individual amplifier stage is not sufficient enough for a particular application. That means we want very high voltage gain that or very high power gain. In that case, it could not be provided through a single stage small signal amplifier, and in that case we need to connect them sequentially. Okay, so there are two way we can have multi-stage amplifiers. One is cascaded and another is cascoding. Okay, in cascading, as we have shown in this circuit, the amplifiers, they are single stage amplifiers, they are connected in series. Maybe at this stage you will not be able to understand what is the advantage, but actually it is used for high frequency applications whenever there is required high gain and low noise. Okay, anyway, so for our interest, that is, there are two types of multi-stage amplifier. One is cascaded, which is normally used, and another is cascode amplification, that is called cascode amplifier, which has a specific application. Okay, so these are the two ways multi-stage amplifiers are there. So important is how we connect one stage of amplifier with the another stage of amplifier. Say what we want is the output of the first amplifier stage, that is actually the AC output, that should be transferred to the input of the next stage. But at the same time, the DC biasing, the Q point, that should not be suffered. Okay, so here, so there is one type of coupling, that is RC coupling. You can see this resistor R, that is RC is there, and the capacitive coupling is there. So capacitor has been used between the first stage and the second stage of amplifier. Here there has been shown self bias network for simplicity. It could be any network, right? Instead of self biasing network, that could be voltage divider bias network, or it could be anything. The idea is, this is a first stage of amplifier and this is the second stage of amplifier, and in between the coupling is provided, that is actually through capacitor, and effectively it is through RC network, right? So this is a coupling capacitor. We know the function of capacitor, that is ideally it is open for DC. Ideal, that is capacitor function, capacitor, that is it is open for DC and it is short for AC. Terminal 1 and terminal 2. Anyway, so here what will happen is, actually AC from the first stage, that will be available to the input, the base terminal of the next stage, but the DC biasing, DC wise, this is just two separate circuit, and that's why DC biasing of the first stage is not going to affect the second stage. Okay, so that is what is the requirement. So this is first type of coupling, RC coupling, right? So if we look at the equivalent circuit, so this is actually our hybrid model for the first stage, and similarly there will be hybrid model for the next stage. On the output of the first stage, you can see there is HOE, which is hybrid model output admittance parameter. Parallel to it, that is transistor has been replaced by the hybrid model. Now parallel to it, from the collector terminal, you can see this is the collector terminal. So from the collector terminal, that is RC1 is there, plus VCC. This is AC equivalent circuit. So VCC is shorted. So plus VCC, that is to be kept parallel. This is grounded. Other terminal is grounded, right? This terminal is grounded with respect to AC. So RC is there and C is there. Let's see how will be the circuit. Yeah. So this is the first stage. The output is via RC1. Next stage, that is you can find here, that is actually the input impedance of the next stage. Okay. Similarly, on the input side, this is Vs, this is source resistance Rs, RB1, that is the AC equivalent circuit part component RB1, and this is actually, you can see, if I have, instead of showing the complete network, if I would show just the simple circuit, this will be Z in, right? Z in of the first stage. Z in of the first stage. Okay. Yeah, so this is going to be the coupling and how the effective circuit will be there. Okay, so the point to be taken care, that is on the input side always, that is the RB1 and this will be parallel to each other, and on the output side HOE is parallel to RC1 and that is parallel to ZE. Okay, we will need this thing when we will analyze this amplifier circuits. Anyway, second way of coupling, AC coupling to be provided is through a transformer. You know, transformer couples only AC. That is, the output of the first stage, that is coupled through transformer to the second stage. But there is DC wise, there is an isolation between the first stage and the second stage. So this is another type of coupling which could be possible. Okay. Third type, that is actually a direct coupling. First we said that this you cannot do this thing. Okay, why we cannot do this? Because see, VCC and this is RB. One, there is some voltage drop across this. This is 0.7 volt fixed and this is VCE. So somehow the biasing that is to be affected. Okay, so but here direct coupling is made possible practically through some specific type of arrangement through which the DC bias requirements, they are matching. Okay, so we don't go into detail of this thing, of this coupling, but just to understand, that is there is a required capacitive coupling, RC coupling, or maybe through transformer, or maybe through direct coupling. That means between two consecutive stages, the DC has to be blocked. Both the stages has to be isolated with respect to DC, but AC output of the first stage, that must be supplied to the AC input of the next stage. This is one more thing which is important, that is all amplifiers, they do have some sort of a frequency. They don't give same response to any frequency. Okay, all AC signals are not considered equivalent, that is they don't have similar response to any frequency. So usually the frequency response is like this, right? It goes like this. So this is the mid frequency range where actually the gain is maximum. So this is a flat response. So it covers some frequency range where almost unity, that is the maximum gain, is provided. So if I show here the curve graph of frequency versus the normalized gain. Normalized gain is A over A max. Okay, so at this point here it is maximum is 1. Okay, so and on both of this side, that will be reducing, the gain will be reducing, and after some frequency almost uh, the gain is 0. That means actually that amplitude is going to be cut down. It will be wave, that is the waveform will be, that is amplitude will be scaled at that frequency. It will be reduced at this frequency. So anyway, so here, so with respect to the maximum frequency, there is a one frequency, or that is two frequencies rather, where we have the A by A max is equal to 0.707, or maybe it is 1 by root 2 of the A max. Okay, 0.707, or you can say it is 1 by root 2 of the maximum gain is there. So corresponding to that, you can find there are two frequencies. This is FL is called lower cutoff frequency, FH that is called higher cutoff frequency, and the difference between FH and FL, that is called a bandwidth. Okay, bandwidth is higher cutoff frequency minus the lower cutoff frequency. Unit is in hertz. Okay, so that means say higher the bandwidth, the it is more it is more benefited usually. Okay, so this is similar curve that has been shown on the log curve, that is 20 log A by mx. Okay, so with respect to log curve, the maximum gain is indicated by 0, and anything which is less than 1, that is negative on the log scale. So corresponding to 1 by root 2 of the maximum voltage gain, that is minus 3 dB voltage gain. So minus 3 dB, that shows FL minus FL and FH. Okay. Okay, so there is one important relationship. Thank you.